Well, hello again everybody, and you can see on the bench today we've got a KAIWEETS HT208D. Now I'm sure that some of you will remember a few months ago I did a review on some KAIWEETS voltmeter probes. Well, a few weeks later after making that video I actually got an email from KAIWEETS and they actually said that they'd seen my little video and they thought it was good. And I've got to admit I was actually pretty gobsmacked that a manufacturer had bothered to write to me and just say that. And they also went on to say that because they liked the video they were going to send me another meter to maybe do a little bit of a review on, but also as a little bit of a thank you. So as I said, I'm actually gobsmacked. KAIWEETS didn't have to do that, and yeah, but thank you very much, it's very kind of you. When I wrote back to KAIWEETS to thank them for sending me this meter, I did say I would be more than happy to do a review. But I did also say that if the meter was good, I would be quite happy to say so. But if I found any problems with the meter or anything that I didn't like, I would also make that known as well. And in reply, KAIWEETS said that that's absolutely fine. Just give it an honest review. Tell us what you think. So here we go. Ricky Ticky Tocks into the box. I bet nobody can remember that show reference on television, can you? Here we go. Unboxing. Oh, we got a hard case. Well, the zip feels okay, doesn't snag and it moves smoothly. If you've watched my previous videos, I very rarely bother to read manuals because my opinion is that a piece of test equipment, in fact any piece of equipment, really it should be designed to be as easy to operate as possible. So you shouldn't really need to read manuals to figure out how things work. Oh, that's my opinion, if a piece of equipment's been correctly designed. Now I have to say this manual is considerably better than actually comes with a number of test equipment items that I've had in the past. It does actually describe quite correctly how to use the meter. Everything's in really good English, it's well explained. In fact the whole of the manual is in English, so rather than just having one page of English and then every other language under the sun, the whole manual, the whole 28 pages, it's all in English and it's all actually very well described. Okay, so here's the information I was looking for, which is actually the accuracy. So this is kind of designed for more high voltage electrical installation work, 230 volts, stuff like that. So typically you don't really care if the meter is accurate to a volt or not in any direction. It's only when you're measuring millivolts and microvolts that you really demand those types of accuracies. Now I can't see that somebody would be buying this type of clamp meter for measuring things like millivolts. The whole purpose of this clamp meter, the main idea behind it is that we can measure high currents safely. That's why you have a clamp meter, but we'll come on to that. So it has listed the specification for the meter and we'll do some testing to check if it complies. Now of course everything comes in plastic bags, so we'll be sure to leave them lying around for any passing children to find. I always think it's a good intelligence test. There we go. Now I'm sure that some of you have spotted that this looks quite different to most digital multimeters that you might have seen on my bench. And of course one of the main differences that you can immediately see is this at the end. So let's just give that a press. So you can see we've actually got these jaws which open and close. Now this is what they call a clamp meter, and the idea behind a clamp meter is that you can actually make non-contact current measurements. So of course you'll know that when you use a traditional amp meter, what you have to do is you have to cut into the circuit and you have to put the meter in series with the current carrying conductor. So the main feature of this type of meter is the fact we don't have to cut into the circuit to make a current measurement. If we've got a wire that we want to measure the current going through, all you actually have to do is you have to open up this clamp assembly, clip the wire in, and then it can make a current measurement. Now there's a few advantages of that. Sometimes it isn't practical to actually disconnect the circuit so you can install your current meter because you might not be in a position to switch the supply off. Certainly if you were supplying something like a house or a machine, you wouldn't necessarily want to switch that off just to do a current measurement. And when you finish making the current measurements, the only thing you've got to do is you just open the clamps and just remove the wire. So as you can see, this really is a major safety advantage if you're working on circuits or maybe control panels that operate at high voltage or where there's a potential for a very, very high fault current. current. Now for working in domestic situations, we don't really encounter very high currents or circuits that can supply very high currents. Typically our plug sockets have a maximum of 13 amp fuse in it. Those plug sockets will be protected in themselves by something like a 32 amp circuit breaker, and in fact the whole supply to my house is protected from a 100 amp fixed fuse. So the most current you could really expect to see is, you know, something in the region of a few hundred amp. But if you were to go into an industrial situation with large control panels, the actual fault currents can be in the thousands of amps. So if something goes wrong when you're measuring something that can potentially deliver thousands and thousands of amps, you really don't want your meter to be able to be connected to it, because all that potential energy is going to go into the meter and it's going to explode. So in the industrial situation, the fact that we can make a non-contact measurement, that's a huge advantage. Whenever you're doing a review of test meter leads, it is in fact the law that you have to do some flexibility testing of the cables themselves, and well, actually they feel absolutely lovely, super flexible, really soft. Now again, I'm wondering if these are actually silicone or if they're kind of that plasticized, is it PVC they use? I'm not exactly sure. Have we got anything written on them? No, there's nothing actually written on the cable itself, which would have been maybe nice to have some information about the quality of the cable. Let's try our KAIWEETS leads. Oh, absolutely fine. So again, I think that these leads are silicone, no damage. And for comparison, let's try some hookup wire, which definitely isn't made from silicone. And you can immediately see when we actually touch the soldering iron to that, it smokes and burns. So taking a close look at the ouchy part of our test leads, I would say that these are actually, well, they're not very ouchy at all. These are pretty blunt. I would probably like to see these being a little bit sharper than this. Now I can also feel just a little bit of a recessed section on the probe end here. So the idea of that is when you're dragging it along, it will actually seat onto a wire. And yeah, these actually do that quite well, so no problem with that. And taking a close look at the probe material, it appears to be kind of bright, a chrome finish. It's not magnetic, so I suspect these probes are probably manufactured using stainless steel. Now I can also see that we've got category 2 1000 volts stamped into the handle of the probe. Now at first sight, a category 2 rating doesn't appear particularly good. Now a lot of people don't seem to really understand these category 2 ratings, and you know, a lot of people just look at the voltage rating. Now the voltage rating I don't really consider that much. Let's face it, these are made from plastic. Anything made from plastic is going to have a good high voltage rating. But what the category 2 part is telling us, it's telling us the maximum energy within the circuit that we can actually measure with these probes. Because if you're not careful, if you was to short something out, you could get a very large flash and a bang. And in fact, the flash and the bang could be so big that it could seriously injure you. So the reason that these have got a low category 2 rating is because we've got all this exposed metalwork which could short out when you're poking around inside a panel. However, just by taking a shroud and placing it over our probe tip here, you can actually see that we've covered up a lot of that metalwork that was exposed previously. So immediately the category of our probe now, it's jumped from being category 2, so it's now rated at category 3 up to 1000 volts, or category 5 up to 800 volts. Now if you are anything like me, you'd be quite tempted to pull these off, because quite often these shrouds get in the way because you can't actually poke your end of your tip here in such a little hole, because the actual shroud makes it that little bit bigger. But really you should keep these fitted because potentially they are lifesavers. Just for interest, let's have a look at this Agilent Probe here. Now this of course would cost several times as much as the KAIWEETS probe here, but I'm sure you'll agree these could actually be second cousins, couldn't they? But looking at the basic category rating of the handpiece here, we can see again that it's only a category 2, just like the KAIWEETS, and it actually only gets extended when we actually fit the shroud tip to it. Now although we did actually confirm that the cable on our KAIWEETS probe here appears to be a really good quality silicon lead, the actual Agilent probe here, it does actually have the voltage rating and the cable specification actually printed along the length of the cable, and I actually do like to see that. It just gives me that confidence factor. And although it may not come out on camera, I can actually see that this Agilent Probe has a voltage rating on the cable itself as 6 kilovolts. It would just be nice to see something printed on the KAIWEETS cable here. Now I guess one of the first things that we need to consider before even switching this on is actually the ergonomics of the meter. So I'm holding the clamp meter in my left hand at the moment, and the actual thumb lever here which opens and closes the clamps, that does actually come to hand quite easily, so that works. I wonder if it works equally well in my right hand. And actually in some ways it works better for a right-hander because we've got a selector switch here, so yeah, can I operate that? Well, the feel of the selector switch is actually very firm and positive. It goes with a real click between the ranges, and it has actually got a soft rubber overmoulding on the top of the switch lever here, but maybe it's because my hands are a little bit sweaty. It's a bit warm in this room. Yeah, I'm having a tendency to actually just slip off that. Certainly we can operate it. Yeah, that is just a bit slippy for me. Tell you what, I'm going to go and wash my hands and try again. I might have something greasy on my hands. So I've just washed my hands. Yeah, that's a lot better. But what I would say, if I was using this meter in an industrial situation, and the sort of thing I would actually be using this for is maybe if I was doing some maintenance on a system that had large electric motors on it, something like that. It's quite likely if I've just changed a motor or done something, I'm going to have grubby, dirty, oily hands. Now I'm not going to bother to go and wash my hands before I make any current measurements. I'm just going to get the meter out and use it. The other thing is I might be wearing gloves. Yeah, I think that this switch could do with, I don't know, there is quite positive ribbing on it, but yeah, it's somehow not quite enough. The switch is actually a little bit small. Now I actually think the function of the switch itself, it's great. It's, as I said, it's really positive between ranges, but there's not quite enough for me to grab onto here. Looking at the labelling on our meter, it does look to be very clear and concise. I have no problem with that. Now, because the meter is likely to be used in an industrial situation, we would expect the labelling here to be resistant to a wide range of chemicals, solvents, greases, etc. So let's try that. So the first thing I'm going to try is just some IPA. Let's give this a rub. Okay, IPA seems okay. The next thing I'm going to try is some acetone, which is obviously a lot more aggressive. No, again, that seems okay. And finally I'm going to try some petrol. No, again, seems to be resistant to petrol as well. Now the meter itself does come provided with some alkaline batteries, but I don't like using alkaline batteries in my test equipment because if you've paid quite a lot of money for a piece of test gear like this, the last thing that you want to do is find that it's been destroyed by, you know, relatively low cost alkaline batteries. So it's my personal choice that whenever I buy a new piece of test gear, I always put lithium batteries in it because lithium batteries, they just don't leak. Comes with a little screw. It isn't actually retained in the back cover, so careful not to lose it. But looking inside the battery cover here, we can actually see that they do use a brass insert, so we're not going to be galling out the plastic whenever we put the screw back in. But I have actually noticed that the back cover itself, it doesn't appear to have any type of sealing around it. And I can also see at the bottom of the battery box here, we do have a battery symbol which tells us what type of batteries to use and, even more importantly, which way round to fit them. And looking at the way it's been moulded into the plastic, it's actually very clear to read, so we're not likely to make a mistake and put our batteries in the wrong way. I can also see printed on the back of the meter, it's got some EN standards which the meter conforms to. So it says it conforms to EN 61010 Part 1, EN 61010-2-030, EN 61010-2-032. Being a brand new meter, it comes with a screen protector, so let's remove that before we switch the meter on. This is always satisfying, isn't it? Oh, there we go. The selector switch here has a very clear off position, and then the first position where the meter's switched on, it's going to come on the 1000 amp range. So let's just do that first. Oh, I wasn't expecting that. Now I'm not actually sure what type of display this is. Is it a backlit LCD? Somebody leave it in the comments if you know, but it is absolutely beautiful, and I didn't realise it's colour. I'm obviously using this meter on the bench, so I've got a perfect viewing angle on the actual display here, but if I actually just rotate the instrument so that I'm kind of looking at it end on, because of course when you're in an industrial situation you might have to present this clamp meter to a cable. It could be in any orientation, so you might not have the perfect viewing angle on the display here, but yeah, that's an absolutely perfect viewing angle, couldn't be better. Here's one of my old current clamp meters. So this one was made by Ferranti, and I suspect this was probably made back in the 1950s. It could even be older than that. Now just for giggles, it might be interesting to do a little bit of a comparison between the KAIWEETS meter here and our old Ferranti meter here. Now the old Ferranti meter here, it seems to have ranges between, I think that goes between 10 amps there, all the way up to 1000 amps. Oh, that's what you call a selector switch. Yeah, that feels beautiful even after 50 or 60 years. Now although there is about 70 years difference between the two meters, in some ways they do share some similarities in that this is also a clamp meter, and again it has this big lever on the side, and you can again open it up here to get, well, potentially even a bigger cable in. Really one of the biggest differences is the fact that our KAIWEETS meter here, this can actually measure DC current. So these old clamp meters, and in fact many of the clamp meters that are still on the market today, they will actually only measure AC, they can't measure DC. Now the fact that this does measure DC opens up a lot of possibilities. Now if, like a lot of people, you're not involved with industrial type electrics on a regular basis, you probably won't need to measure currents up to 600 amps. In fact, you probably would never need to measure them up to 60. You're going to be interested in measuring just a few amps. But the reason I think the KAIWEETS meter is such a game changer is the fact that not only will this measure AC current, it will actually measure DC current. Of course, I also like to restore old cars and trucks and things like that. So the fact you can measure DC with this would make it really useful in automotive applications where you may be looking for things like faults with starter motors or dynamos or generators, or maybe where you're just trying to identify why fuses are blowing or something like that. You could very easily just insert a wire into the jaws here without having to cut into the circuit, because that's the problem with using a traditional ammeter, isn't it? You've got to cut into the circuit, but the fact that you can just open the jaws, slip a wire in and make a current measurement, that could be really useful for automotive diagnosis, couldn't it? I think we'll start off by taking a look at the very lowest AC current measurement that we can make. Now unfortunately I don't own anything as advanced as a current calibrator, so what we're going to do today, we're going to use this soldering iron as a load, and we're going to feed that load through a variac here so we can control the voltage going into the soldering iron, and because it's a resistive load, the current that it draws is going to be proportional to the voltage. And we're going to use our Agilent meter here, which is capable of making very accurate AC measurements. We're going to kind of use this as a transfer standard. I'm going to start winding up the voltage now, and we should see the current increase on the Agilent meter here. So we have a set current now of 10 milliamps, but we don't have anything displayed yet on the KAIWEETS meter. Now I'm not totally surprised by that, because looking at the current specification for this range, it actually says 2.5% of the reading plus 5 counts, and as we saw in last week's video, that 5 counts can actually make a huge difference, and in this case 5 counts could be as much as 50 milliamps. Just over 20 milliamps set, and still nothing on the KAIWEETS meter. 50.4 milliamps now, 60.4 milliamps. Now although I haven't done the maths, we're actually 6 counts over for the 5 counts specified in the meter specification, so really we would be expecting to be seeing a display now, and we're not. 90 milliamps now, and it is trying. I'm just wondering if the Y position is going to make any difference. Nope, doesn't seem to. Finally, with a set current of 110 milliamps, we're getting a consistent reading on the KAIWEETS. So we are within a few counts. We're within 5 counts of these meters, but it's a little bit disappointing that it doesn't actually start reading until we've got 100 milliamps. So this last decimal place here of resolution is really not doing us very much good at the lower end of the scale. As you can see, I'm in trouble because I borrowed the kettle, but kettles full of water make excellent resistive dummy loads, so that's what we're going to use now. We're at just over 500 milliamps now, and our KAIWEETS meter is in fairly close agreement. We're just a couple of counts out at 480 milliamps. At 1 amp we are within specification. We're flicking between 3 and 4 counts out. Now the final current I can set is really limited by the performance of my Variac, so that's going to be 2 amps. So let's go ahead to 2 amps. And at 2 amps, occasionally the KAIWEETS meter is 1 count out, but really they are in close agreement now. So I've just gone ahead and I've switched all my test gear on in my room, and let's have a look at what we're drawing here. So it says we're drawing about 1.2625 amps, and we've actually got the clamp meter around the live wire at the moment. So that's the current flowing into all my test gear. We can also go ahead and just grab the neutral, the return wire. And of course that current is pretty much the same, because the amount of current flowing away from our test gear should be the same as the current flowing into it, unless of course we've got some form of earth fault, in which case we'd actually get some current flowing through the earth line here. Now, because most of our test equipment on the shelf, it's going to be fitted with filters within inside that equipment, so there's going to be some capacitors between the live wire inside the equipment and the chassis. So I know for a fact that there will be some current flowing into the ground system. Now, some of the main uses that I've had for using clamp meters in the past is to actually try to track down some of these stray currents and finding out why my main supply is tripping out. Now, you may think that the way you would do that is just by clipping onto the earth wire like this, and of course you could do that, but typically that's not the way it's done. A better way to do it is to look for the imbalance in the current flowing into the system and the current flowing out of the system, because they should both be the same. Now, if you actually put your clamp meter across both wires here, the live and the neutral, you should get 0 on the meter, because in theory you'll have no imbalance between the current going into your equipment and the current coming out again. So you should get a reading of 0 on the meter. Now we can also just clip onto the earth, and again we can see that the reading is actually 0, but unfortunately I don't quite trust the reading that we're getting here, because as we saw, unfortunately this meter at very low currents, it does lack some resolution. It's not sensitive to these very low leakage currents, but I do have another clamp meter that is actually designed for that particular purpose, so let's just take a look. So this clamp meter is made by Alphatec, and for those playing along at home, it's the Alphatec Tech 775. Now it is actually a little bit unfair to actually compare the Alphatec meter here to the KAIWEETS meter, because this particular meter is designed for actually measuring these very low leakage currents, and so it does have a 200 milliamps range, whereas our KAIWEETS meter, the actual lowest range it has is the 6 amps range. So I'm going to clip onto both our live and neutral wires again. Now this time we've actually got a reading here, and it's fluctuating a little bit, but hopefully you can see that it's about 3 milliamps. So I've actually got 3 milliamps of difference between the currents going into the test equipment and the current coming out of it. Now that current is actually going somewhere. Now in theory it's probably going directly into this earth wire, so let's actually measure that. Measuring about 2.6 milliamps, 2.7 on the earth wire itself. So you can definitely see we do have some current flowing into the earth system, but the KAIWEETS meter, because it doesn't have the resolution, it couldn't actually see it. For those of you that are wondering why I actually prefer to put the meter around both the live and the neutral wires to measure the imbalance, why I do it like that, it's because for a piece of equipment maybe that's manufactured from metal, then some of that residual current, it might not be flowing down the earth wire. If it's a piece of metal bodied equipment that's sat on the floor, some of that earth current could be going directly into the floor, in which case it won't be flowing down the earth wire, but you will still see the imbalance if you measure between the live and the neutrals, as I did here. So if you're looking for earth leakage currents, this is a better way of doing it than just monitoring the current in the earth wire itself. Actually, one slight problem I have found with the unit is that under bright daylight conditions the actual display can be a little bit bright, and it's actually so shiny it does tend to reflect things in the surface. So this is my milling machine, and I know that you've seen this many times before, and it's supplied by the Warco company here in the UK. Now at the top of the machine here you can see a large three-phase motor, and this three-phase motor is actually used to power the spindle for the machine and do all the cutting. So this is the main electric motor, and as I just mentioned, it's a three-phase motor, but here in my domestic garage I've only got a single-phase supply. So if we were to look in the control panel at the back of the machine, what we'd actually find is a variable frequency drive, and that takes the single-phase power supply from my house and it actually chops it up and converts it into three-phase, which this motor requires. Now, apart from doing the conversion between the single phase and the three-phase, the actual variable frequency drive, well, the clue is in the name. You can actually change the frequency of the power going to the motor, and you can control the speed of the motor by changing the frequency of the supply to it. So let's just switch on and I'll just give you a quick demo. So we can go from a very low speed And another useful feature of the variable speed drive is we can actually reverse the direction of the spindle. So I've just removed the lid from the terminal box of our three-phase electric motor, and you can see that we've got three wires here. We've got a grey, a black and a brown. Each one of those is one of the three phases which has been supplied from the VFD to this motor. Now, if we were to have a look at the voltage waveforms with an oscilloscope, what we'd find is that they wouldn't be sinusoidal like we're used to looking at. They would be closer to being some kind of square wave shape, and that's because the way that a VFD works, it takes the incoming main supply, it rectifies it, and then it chops it up again, and it supplies that chopped up DC to the motor. Now, quite a lot of current measuring meters and voltmeters, they're actually expecting to see a sinusoidal waveform, and if they don't see a sinusoidal waveform, they can become quite confused and basically give you nonsense on the reading. The other thing that we would find is because the supply is actually being chopped up, it looks very, very noisy, electrically noisy. So noisy, in fact, that a typical voltmeter or current meter, it would have trouble locking onto the true signal, and again it would just display nonsense. So one of the main features of our KAIWEETS clamp meter is the fact that it does have this special Vfd mode, which really just consists of a low pass filter. So basically it can filter out all that chopped up noise and display a true reading. And another advantage is that we don't actually have to disconnect the actual wire from the motor terminal here to make a reading. All we have to do is clip round this wire. But unfortunately in this case we would actually have to disconnect the wiring because there isn't quite enough wire here. The loop of wire that she's given us, it's just not quite big enough to get the head of the clamp meter onto it, unfortunately. So rather than making the current measurement from the terminal box here, which is what I intended, we will have to make it in the supply cable to the machine. We've got both the Fluke 25 and the KAIWEETS clamp meter installed in the supply line to the milling machine, so let's go ahead and start it up. Oh, and unfortunately everything went off. I've actually made a really silly mistake. Can anybody spot it? I wanted to actually use the 10 amp measuring function on this meter, but I haven't used that. I've actually plugged in the wrong terminal. I've actually got it plugged into the milliamp input. I should have had the meter plugged into the 10 amp input here. So what happened was when we switched the machine on, it actually blew the 200 milliamp fuse in the meter, and that disconnected the electrical supply going to the milling machine and everything went off. Now, although for me this is quite annoying because I now have to replace a fuse in the meter, I think it also gives you a good example of why making non-contact measurements using a clamp meter, it's a safer way of doing it because you're less likely to make this kind of silly connection error. So I've just engaged the hold feature in our clamp meters, but you can actually see that the readings are quite different. The Fluke 25 meter is measuring an awful lot lower. It's about 1 amp lower, and the reason that we're getting such a difference between the Fluke meter and the KAIWEETS meter is because the Fluke meter is actually getting quite confused because there's so much electrical noise on the AC line which is being generated by our VFD, whereas our KAIWEETS meter is indicating 3.4 amps. Now this is much more likely to be reliable because it's using its special low pass filter function to actually remove the noise from the AC supply line. I've got set up on the bench now a large transformer. Now the thing about this transformer is I know that when we actually plug this in and switch it on, it actually has a high inrush current, and I know that because when I switch it on, all the lights flicker in my garage as this hungry transformer gobbles up all the available current in the circuit and the lights go dim for a second. Now another really useful feature of the KAIWEETS meter here is the fact that it has a specialist measuring function which is called Inrush. Now Inrush is actually different than the max hold function that you've seen on digital voltmeters, because the problem with the max hold function is generally it's quite slow. The actual measurement has to be present for quite a while before the meter will capture it, whereas this meter has been specifically designed to catch these high inrush currents. We can see with our transformer switched on and without any tools actually connected to it, our transformer is still drawing 1.78 amps of current from the mains, so this transformer would actually appear to be quite a high loss transformer. So we're actually putting 1.78 amps into this transformer and we're getting no useful work out of it, so all that is effectively its loss, so it's all inefficiency. And if you've watched some of my previous videos, you'll actually know that these losses are actually iron losses within the transformer itself. But let's have a go now at measuring the actual inrush current to the transformer. So I'm going to switch it off. We've got to press a function switch to actually engage the inrush function. And we get all blanks here on the meter screen, so I'm going to switch back on. Hopefully you saw the lights flicker when I switched the transformer back on there, but you can actually see our inrush current, it's actually 59 amps. Wow, 59 amps, that's actually quite a lot of current, isn't it? Now when you switch on and off the transformer, you can actually get quite a variance in the inrush current because it depends at what part of the voltage cycle you are when you actually switch the transformer on. If you're at the zero crossing point, you'll find that the inrush current will be quite low. But if you happen to be at the top of the 240 volt waveform when you switch the transformer on, that 240 volts is applied directly across the transformer windings. Now there isn't actually a magnetic flux there at the time, so that transformer winding, it doesn't look like an inductor, it actually just looks like a piece of wire. It takes time for the magnetic field to build up within the transformer, so that's why you get such a high inrush current, but as soon as the actual core has been magnetised, very quickly that current drops away. So again, if we actually just go back to the standard measuring function, again we'll find that the actual standby current for this transformer is not very high. And again we're now back to our 1.7 amps of quiescent current. And once again. So this time the inrush current was much lower at only 14 amps, and that's because the main cycle was actually closer to the zero crossing point than it was to the 240 point. So let's take a look now at DC current measurements. And as we did before, we're going to use our Fluke 25 meter as the reference, and we have this directly connected in circuit with the supply. And we've got the KAIWEETS meter, and that's been set to its DC current measurement range. We've got the Alphatec meter, and we've also got my old Ferranti meter. You can see that both our Fluke 25 and the KAIWEETS meter are actually displaying the same current, which is 2 amps, which is what we've got set on the power supply. But both our Ferranti meter and the Alphatec meter here, they're both actually displaying nothing, no current at all. Now the reason that both our Ferranti meter and the Alphatec meter, the reason that they're not displaying anything is because the way in which they sense the current which is flowing through them. Now although at first glance it might not be obvious, both of these instruments are what I would call transformer based. So you've actually got a transformer, and in this case let's look at this one. So we've got a transformer and we've got one turn on the primary, then the secondary part of the transformer, which is inside the instrument here, inside the box, we've got another coil of wire, and that coil of wire is actually just connected to an ammeter here. Now I'm sure that all of you know that transformers, they won't actually work with DC. you need to pass AC through them for them to work, because if you just put DC through them, what will happen is the actual core within the transformer will become magnetised, it will saturate with DC, and you won't actually get any transfer of magnetic flux between the primary and the secondary side, so the meter movement won't operate. So these are AC reading meters only. Now I actually think it's quite amazing that our KAIWEETS meter here is able to give a DC current measurement when our other two meters here aren't able to do that. Now of course the reason that it can do that is because the sensing technology which is built into the clamp here, it's quite different than the one employed by these other two meters. Now if we just take our Ferranti meter out of circuit, you can see that we've got these tongs here, but what we've got is effectively a circular lamination. So if we look at the ends of the tongs here, you can see that there's a metal contact and there's another metal contact there, so it's metal on metal. You have to have this metal on metal contact for the magnetic flux to be able to flow easily around the circuit. Now it's actually the same for our Alphatec meter, so if you look at the jaws in there, we've got a piece of metal and we've got another piece of metal, and these two pieces of metal slot together. But if we just disconnect our KAIWEETS meter from circuit, and again hopefully you can see the jaws there, got a piece of metal there, but on the opposite jaw of the meter there's not metal, there's actually just a piece of plastic. Well, what's actually behind this piece of plastic is a Hall effect transistor. So what this meter's doing is, rather than acting like a transformer, it's actually directly measuring the magnitude of the magnetic field which is flowing around here. So it's taking a direct measurement of that magnetic flux, or probably better to call it a Gauss. So because this meter's based on a Hall effect transistor which directly measures the magnetic field rather than relying on a transformer, that's why the KAIWEETS meter is able to measure DC when our other two meters can't do that. So just the same as the AC current measurement range, it appears that the DC measurement range starts working about 100 milliamps. But below 100 milliamps, our first digit here really doesn't appear to do very much. At 500 milliamps, we're just 2 counts out, and at 1 amp, again, we're just a few counts out. At 5 amps, we're spot on. And with a set current of 10 amps, we do appear to be about 14 counts out. But in fairness, I also can't be certain of the calibration of my Fluke 25 here. With 15 amps set, the KAIWEETS meter is just 2 counts low, and with 20 amps set, my cables are now starting to smoke. Now if you have a clamp meter but you're actually struggling to measure some very low currents, there's actually a little trick that we can employ to make the meter more sensitive. So the clamp meter is effectively measuring the magnetic field which is kind of being given off by our wire here. So what we can actually do is we can actually increase the level of that magnetic field, and the way we do that is simply we're going to put more turns of wire around the clamp jaws here. So let me do that. We've got 1 turn at the moment, so I'm going to open up the jaws. So 1, 2, 8, 9 and 10. So rather than having 1 turn of wire, we've now got 10 turns. So effectively we've increased the sensitivity of our meter by a factor of 10. So rather than reading 0.1 of an amp, it's actually reading 1 amp now. The KAIWEETS meter also has a 1000 amp range. Well, it would seem rude not to test that, wouldn't it? So let's give that a go. I think we're going to need a thicker wire. At 100 amps, we're 2 counts out. At 500 amps, we're 2 counts out. I'm going to test the 1000 amp range next. The problem is everything's likely to get quite hot, smoky and melty in here. So we can only do the test very quickly. But that does give us the opportunity to try this max function. So let's give that a go. Max. 1000 amps, here we go. And at 1000 amps, we're just 5 counts out. And if anybody can tell me where you keep the 1000 amp fuse in a Fluke 25, leave it in the comments. Now the main reason for buying a clamp meter is for current measurement. But our KAIWEETS meter can also measure voltage, and it has a 600 millivolt, 6 volt, 60 volts and 600 volt ranges. Let's start by measuring DC volts, and we're going to use a PDVS2 Mini to provide that voltage. On the 600 millivolt range, the highest resolution or the lowest significant digit here is 0.1 millivolts, so let's try that first. With 0.1 millivolts set, we don't actually have an indication showing on the KAIWEETS meter, but the basic accuracy on the voltage range is 3 counts, so let's increase that. Okay, and it has now started to read, so the measurement is within just a couple of counts. Let's increase that. Again, within 3 counts, within 3 counts. And with 1 millivolt set, we are within 1 count. Let's try 10 millivolts. Again, within 1 count. 100 millivolts. Spot on. 1 volt, also spot on. And at 10 volts, also spot on. And at 250 volts, both of our meters are in perfect agreement with each other. So let's do 500. Now we are only outputting 491 volts, but again, our meters are in perfect agreement. The KAIWEETS meter has a maximum voltage of 600. However, I'm interested to see what happens if we put 1000 volts into it, so let's try. But both of our meters are in agreement at 823 volts. We're now going to test the AC voltage range. Unfortunately, the lowest AC voltage that I can set is 100 millivolts. But as you can see, both the meters are in perfect agreement. And at 1 volt, our meters are in agreement. And at 10 volts, we're 1 count out. At 100 volts now, our KAIWEETS meter is just 1 count out. At 200 volts, we're 2 counts out. And at the maximum voltage which I can set, which is 294 volts, we're just a few counts out. So I think that the DC and AC voltage accuracy of the KAIWEETS meter is excellent. Now just a couple of small observations. When we actually switch the meter on to the voltage range, I've noticed that it does always start up in DC volts. I think that this is more likely to be used as an electrician's meter, so personally I think it would be better if it actually started up in the AC voltage range. So you'd have to select that here, and of course it does go into AC, but I think it would be better if it actually started off on AC whenever you selected volts. But a more significant problem that I found with the KAIWEETS meter is that when we're actually in the current range, if we have any connections made to the meter here for the voltage input, it actually affects the current range. So at the moment you can see that we don't have a wire going through the jaws and it's showing 0, 0, 0. That's what we'd expect. But if I actually just turn on a voltage supply to these terminals, you can see that the meter starts indicating 3.6 amps. So we shouldn't be seeing a meter reading here at the moment, and if by error you left the meter connected to a source of voltage, it would clearly affect the current measurement here. So that affects my confidence in the meter's ability, and that could perhaps lead to an unsafe situation. I've been having a look at the specification for the KAIWEETS meter, and I don't see that it specifies the bandwidth of the AC volts range. Now for typical domestic and industrial installations, I would expect the frequency to be specified at probably 50 or 60 Hz, but because this meter is designed to work with variable frequency drives, I would expect the frequency to be extended from that to maybe as low as 10 Hz to maybe up to 200 Hz. Now at 50 Hz both of our meters are reading within a count of each other, so that's pretty good. And on the AC voltage range, the KAIWEETS meter will also indicate the frequency, and it's flicking between 49.9 and 50 Hz. Let's drop the frequency now to 10 Hz. I can see that the frequency indication on the KAIWEETS meter is now showing 10 Hz, and the actual voltage difference between the Agilent meter here and the KAIWEETS is just out by a couple of counts. The frequency now shows 200 Hz and the meters are within 1 count. 500 Hz is indicated on the KAIWEETS and the meters are within 2 counts. 999 Hz is indicated and the meters are within 5 counts. 2000 Hz is indicated on the KAIWEETS and it's within 2 counts. At 3000 Hz the indicated frequency is correct, but there's actually now a serious error in the voltage reading, in that it's dropped by about half a volt. So I'm going to say the maximum usable frequency for the KAIWEETS meter is 2 kHz. The frequency range for the KAIWEETS meter does vary depending on what mode you have selected. And when the voltage mode is selected, the frequency range is between 10 Hz and 10 kHz. As you can see, the frequency reading is correct at 10 kHz, but of course the voltage reading isn't. Let's see what happens if we increase the frequency outside of the meter's specification to above 10 kHz. And at 15 kHz the frequency reading is perfect, and 20 kHz is indicated without any problems. And 50 kHz is also correct, as is 100 kHz. And finally, at a set frequency of 120 kHz, the meter's starting to have a problem, but this is actually exceeding the meter's specification by, well, more than a factor of 10, so no complaints there. Now, if we actually put the KAIWEETS meter into its Hertz range, you can actually exceed that frequency with a maximum frequency in the Hertz range of 10 MHz. So let's give that a try. So at the moment we've got 120 kHz set, and that's reading pretty perfectly. And at 10 MHz now we can see that the frequency reading is just one count out, so that's pretty good, isn't it? Now, I've also just noticed at the top of the display here we've got the duty cycle, and that's another useful feature that I wasn't previously aware of. Previously, when I was using the meter in the AC current range, I noticed that although it was measuring the current correctly, it also has a frequency display here in Hertz, but for whatever reason that frequency display always remained at 0, and I actually assumed that that was some kind of a fault or a bug, but according to the meter's specification the frequency indication won't operate until we're actually measuring a current above 25 amps. But let's go ahead, wind the current up, and we'll find out at what point it starts working. There we go, so the actual frequency display, it actually appears to kick in for this particular meter at about 16 amps. But again, 16 amps, that's a very high current to enable the frequency measurement to work, so yeah, I think that should read lower. A meter of this type is primarily designed for its current measurement capabilities, but surprisingly the KAIWEETS meter does have a very good resistance range, and that goes from 600 ohms to 60 megohms and is split into 5 ranges, with the best resistance resolution being available on the 600 ohm range, which is 0.1 of an ohm. And the accuracy for the resistance range is plus or minus 1% plus 5 counts. Okay, nothing for 0.1. But it does start reading at 0.2 of an ohm. Between 0.1 ohm and 1 ohm, the meter reading was within 1 count, so that is actually very good for a meter of this type. At 10 ohms we're just 1 count out, at 100 ohms we're just 1 count out, and at 1000 ohms we're just 1 count out, and at 10,000 ohms we're 1 count out. Now my 100k resistor is actually 99k, and at that we're just 1 count out. At 1 megohm we're 5 counts out. My 10 megohm resistor is actually 990k, so we're just 1 count out. The highest resistance value that I have to hand is 21.8 megohm, so let's try that. And we get a reading of 21.9, so that's pretty damn close, isn't it? Now let's also test the resistance of the leads that the meter comes with. And these leads do actually come up as 0 ohms, so they must have a reasonable amount of copper in them, so that's good. Now from time to time it's not unusual to have to extend the length of your test leads, and of course that increases the resistance, so I'm just going to simulate that effect of having long test leads by setting up 2 ohms here on my resistance decade box. But it is really useful to be able to remove this 2 ohm offset from our meter reading, and the way we do that is to use a 0 or a null control. So I can see here we do have a 0 button, so let's just try that. And that in fact does allow us to zero out the resistance of the test leads, so that's great, I have no problem with that. Now of course no multimeter review would be complete without doing the resistance beep test. And I would say that that's actually pretty fast, and it's also the type of beep which is latching, so it doesn't matter if you only kind of just stroke them for a few moments, it still actually gives the same length of beep noise. Now, as well as a digital indication of the resistance value, our meter also has a continuity indication lamp. And when the meter sees a resistance of less than 60 ohms, we get a first stage indication here in red. But if the resistance then continues to fall to below 30 ohms, we then get a green indicator and the continuity beep. Now I I actually think that continuity indicator lamp, I think that's a useful feature, because if you were to be using this meter in a noisy industrial environment, it's quite likely you wouldn't be able to hear the bleep with a lot of machines and things running in the background. We also have a diode test function, so we may as well give that a try. Now I'm sure that you'll already know, but when we're in the diode test range, the meter's going to indicate the forward voltage drop across the diode. So let's start off with a germanium diode. 0.4 of a volt. Let's try a Schottky diode, I'd expect that to be a bit lower. 0.29. Let's try a silicon signal diode. 0.63. Let's try a power diode. 0.61. And we do also have some LEDs that we can test, which are going to have a higher forward voltage, but we can also see if the meter can output enough current to actually illuminate these LEDs. Now I suspect that it will, because I've measured the output current from the meter and it's about 2 milliamps. And that's illuminated with a voltage drop of 1.8 volts. Let's try our yellow. Well, the yellow LED is just about illuminating. It's not very bright though, but the forward voltage drop is 1.7. Let's try the green. And again, it lights up very faintly. The forward drop is 1.8 volts. And finally, we'll try the white LED. So this should have the highest forward voltage of about 2.6 volts. Let's try that. And we have a forward voltage of 2.6. So as you can see, it can quite easily light up a white LED. And at the far end of my test board, we've got a transistor, so we should just be able to detect a silicon transistor junction, so let's try. And that's got a forward voltage of 0.72. And as you just heard, when the meter detects a good diode junction, it gives us a bleep. Let's test the capacitance range next. And the capacitance range is between 10 nanofarad and 10 millifarads, with an accuracy of plus or minus 4% plus 5 counts. Because I've got a range of capacitors here, we'll start the test at 10 picofarad. Okay, nothing, but that's not unexpected, that's outside its range. Let's try 100 picofarads. Okay, we do actually get a reading there, 92, so actually that would be within spec. Let's try 1 nanofarad, bang on. Let's try 10 nanofarad, 10, no complaints there. Let's try 100, 100.8, pretty good. Let's try 1 microfarad, 999, that's good enough for me. Let's try 10 microfarad electrolytic, 10.5, 100 microfarad. Now I have noticed that measuring these higher capacitance values, the meter really does slow down in taking the reading. It is quite a long period to wait. And finally 1000 microfarads. Okay, we're waiting. Anytime you're ready. Okay, 984, 89 and climbing. So it's obviously having a little bit of trouble charging up this capacitor, but it is 1000 microfarads, so I'm going to call that good. On my bench here I've got a 2-core cable, and it's got both a black core and a red core. And the cable itself is about 5 meters long. Now our 2-core cable, it's almost certainly not actually rated for 230 volts, but I'm not going to let that stop me. So we're actually going to take the red core of the cable and we're going to connect it to the live 230 volt supply. Now we've also got a black core here. I've actually cut that short and we're not going to connect that, so let's just fold that out of way because we're not going to use it. So here we are, here's a red core. I'm going to connect it into the circuit now, to the live, and now we're going to close up the smart block, and now we've got 230 volts onto this red wire. Now at the other end of the wire we've actually got this red Vargo terminal, which is just protecting me from this live red wire. And we've also got the black wire, which actually isn't connected to anything at the moment. If I take the red wire here and just measure the voltage on it, of course we're going to see my domestic supply voltage, which is normally about 245 volts AC. There we go, 245. If we take the black wire now and measure the voltage on it, what would you expect to see? Remembering it's not actually connected into circuit, well logically I would expect that we wouldn't see anything, but let's try that. But what we find is the meter's indicating that we've got a voltage here of 206 volts. Which is really strange, because if this wire did have 207 volts on it, you'd expect if I hold it I would get an electric shock, but I don't. So what's going on? So we had a 245 volt supply here, and we had that connected to a red wire. So let me just mark that as red there. And then I'm just going to draw in a neutral wire, which is our return path, because you need a circuit return. And the first thing we did is we actually took a voltmeter, so I'm going to draw a voltmeter there. Put V for volts, and we measured 245 volts, didn't we? Well, that's not unsurprising. Now, as well as a red wire, we also had our black wire, so let's draw that in. I'm going to put B for black at the bottom of there. Now, the black wire wasn't actually connected to anything. It wasn't connected to the red wire, it wasn't connected to the supply, it was disconnected, it was just floating. But something strange happened. When we put our voltmeter into circuit now, we measured a voltage. We wouldn't expect to see anything, but we actually measured 207 volts. What I want you to do now is take a look at this long red wire and the long black wire. And we've got two wires here running in parallel with each other, and they're actually separated by an insulator. Does that remind you of anything? Let me just redraw it, give you a clue. So here's our little red wire, here's our black wire. Any ideas? Now, we connected the black wire here, didn't we, to the voltmeter, so I'm just going to draw a connection to the voltmeter, V. And then our red wire here, just this little red wire, that was connected to our main supply, so that had 245 volts on it. So hopefully you've spotted what we've actually formed here with our red and our black wires running parallel with each other. We've actually formed a capacitor. Now, of course, we know that DC can't flow through a capacitor, but AC can, so we're getting an AC current now, which is actually flowing through our circuit. Even though the black wire isn't connected to anything, the fact that the two red and the black conductors, the fact they're separated by this insulator, we form this capacitor, that's going to allow some AC current to actually flow through our circuit here into our voltmeter, and that's why we're getting a reading on the voltmeter. Now, the magnitude of the current that's flowing in our circuit, it's going to be dependent on the value of capacitance. Now, if our red and black wires are running parallel with each other for quite a long distance, the value of that capacitance is going to be relatively high, and that's going to drive the current that's flowing in our circuit, and that's going to increase the voltage reading on the meter. Whereas if the distance that the red and the black wires run together is relatively short, the actual capacitor formed is also much smaller, and of course the current then flowing in the circuit will be smaller, and the voltage reading will also be smaller. If we know the value of the capacitance between the two conductors, we can work out what the reactance is of the capacitor. And what you'll find is the reactance of the capacitor here, it actually forms a potential divider with the actual input impedance of the voltmeter. In this case, the KAIWEETS meter has an input impedance of 11 megohms. So using that 11 megohms and also the value we've worked out for the capacitive reactance, we can work out the total circuit impedance, which as it happens works out to be about 12.67 megohms. Once we know that, we can divide it by the voltage to find the current which is flowing down the circuit, and then we can do a simple substitution to actually work out that the voltage here across the 11 meg resistor works out to be about 212 volts, whereas what we actually measured was 207. I'm going to call that close enough. So we've just demonstrated there how in an AC circuit the capacitance between one conductor and another, it can actually lead to induced voltages. In most cases the currents that give rise to those voltages are absolutely tiny. Now, in the case of a modern digital voltmeter like this, because we have such high input impedances, even those very small currents can give rise to quite a significant voltage indication on our meter. Now, because this effect is caused by stray capacitance within the cabling, it only affects AC and not DC circuits. But there is a different situation that can occur in DC circuits that can give rise to what we call these ghost or phantom voltage measurements. On the bench here I've got another red and black cable, and as before I've actually connected the red cable here. That's connected to my 12 volt power supply, and you can see that this actually runs through to a connector block. Now, the black wire isn't actually connected to anything, so if we take a measurement of the voltage on the connector block here, we're going to see 12 volts. And we're not going to see anything on the black wire, and of course we're not going to see anything on the other end of the black wire either. Now just to make things easier for me, I'm just going to connect our voltage probe here. I'll just connect it to the black wire. And you can see that the reading effectively settles down to nothing. So of course, under this situation, we've got the two wires separated. Because it's DC, there is no capacitance effect, so we're not getting any stray capacitance giving rise to currents flowing. So our voltmeter here, it's not actually indicating anything. But one problem that we do get in DC circuits, and especially in automotive circuits where things like the wiring inside a car or truck, they're exposed to the elements and quite often the cabling will get wet. Well, what can happen is if the cabling gets wet, and especially if connectors get wet, the insulation breaks down. So let's simulate the ingress of moisture by dropping our connector block here into a large gin and tonic. But you can see now that even though our red and black wires, they're not actually physically connected to each other, the actual voltage has shot up to, well, just under 12 volts. So let's just take the connector block out of the water. And of course the actual voltage reading has dropped back a bit because we were getting a lot of conduction through the water itself, but we still have a conduction path here because the connector is wet. When this connector dries out totally, the reading will probably fall back to zero, but while it remains moist like this, we're going to be getting conduction through that moisture, which again is leading to this stray voltage or this phantom voltage being indicated on our cabling here. So we've seen the mechanisms now where stray capacitance in an AC circuit or resistance within a DC circuit, but of course you can also get moisture and resistance in an AC circuit as well. But those resistances, they actually form a potential divider with the very high input impedance of the voltmeter, and even though we have really little tiny currents flowing into our voltmeter, the voltage indication can still be much higher than we would expect. And they actually call these misleading measurements, they call them phantom or ghost indications because they aren't indicative of the true voltage flowing in the circuit. Now wouldn't it be nice if the meter had a feature that would allow us to change the input impedance of it? So rather than the currents flowing here into the voltmeter, if we could actually divert those currents away somewhere so they wouldn't cause a false indication. Well, our KAIWEETS meter does actually give us a mechanism for changing its input impedance. So you can just imagine here that where we've normally got the 10 megohm input impedance of the meter, I'm just going to draw another wire. I'm going to draw a switch on there. There's a switch. And then I'm going to draw another resistor. And this resistor is effectively, it's connected in parallel with a 10 megohm resistance there. And this resistance is 30 kiloohms. Now what we can do with a KAIWEETS meter, in the voltage measurement mode, we can actually select a special range that they call low Z. And what that does, it actually brings this 30 kiloohm resistor into circuit. It puts it in parallel with the 10 megohm. So rather than having an input impedance of a meter that's 10 megohm, when we actually close this switch, the actual input impedance will drop to 30k. So now this very tiny current, rather than going into the voltmeter, it's going to take the easiest path and it's going to flow through this 30 kiloohm resistor instead, and that's going to result in this voltage dropping quite markedly. I'm using my flute meter here to measure the input impedance of the KAIWEETS meter, which is set to the voltage range. And as you can see, the input impedance of the KAIWEETS meter is just above 11 megohm. However, if I now put the KAIWEETS meter into its low Z voltage measurement range, we're going to see this resistance figure drop. And in the low Z voltage range, you can see that the input impedance is actually closer to 30 kiloohm now. As we did previously, I've taken my 2-core cable and I've connected the red cord to the actual AC supply here. And we've got the KAIWEETS meter in its standard voltage measurement range, which means the input impedance is about 11 megohm. There you go, 246 volts, and on the black wire we've got a voltage measurement of 211 volts, even though this black wire isn't connected in circuit, it's only connected via the capacitance. So let's engage the low Z function now. So as you can see, the incoming supply on the red wire is just the same, 246 volts. But when we measure the black wire, now the voltage has dropped, it's dropped to just 17 volts now. So we can actually see that this much lower 30 kilo ohm input impedance, it's pulling that voltage right down. So using this low Z function, we can have a pretty good idea that the voltage that we're seeing here, it's a ghost or a phantom voltage. And it wasn't a true indication regards the energization of the circuit. When using the low Z function, the input impedance of the meter won't be its standard 11 megohms, it will be around 30 kiloohms. So what that actually means is there'll be a lot more current flowing in your circuit when you're taking your measurement. In the case of a 245 volt supply, we can simply do Ohm's law. So for a 10 megohm input impedance, we'd actually have 24 microamps of current flowing in circuit. But when we have the low Z measurement selected, because we've got 30 kiloohms rather than 10 megohms, the actual current flowing in the circuit will be 8 milliamps. So that's an awful lot more current. Now of course that's exactly what we would expect for more current to be drawn from the circuit. But for example, you wouldn't want to use this range for taking sensitive voltage measurements on high impedance circuits, maybe measuring the voltage across resistors on a PCB, because this actual 30 kiloohms will actually load the circuit under test and you will get a very false reading. And another thing to consider when using the low Z range is whatever your supply voltage happens to be, which in this case is 245 volts, you've actually got 245 volts here across a 30 kilo ohm resistor. Now if you actually do the maths, which is V squared over R, you can actually calculate that we've got 2 watts of power now being dissipated in that resistor. So what's going to happen is this resistor is going to get hot, and for that reason KAIWEETS specify that you can only use the low Z measurement for up to 1 minute maximum. Well, with the aid of a very large gin and tonic, let's go ahead and test the temperature measurement capabilities of our KAIWEETS meter. Also included with the meter is a set of thermocouple probes which we can use for external temperature measurement. Now at the moment I've got the KAIWEETS meter, it's set to DC amps and it's on the 1000 amp range, but we can also see that it is actually displaying a temperature of 20 degrees on the meter here. So it's a dual display, it's got the actual current reading at the bottom in the big letters, and then it's got the small letters which are just showing the temperature measurement. Well, this meter has been in the refrigerator for about half an hour, so it actually does feel cold to the touch. So I know that this temperature should be a lot lower than the 20 degrees that's being indicated. So I think that this is some form of false indication. I don't think that this meter has an internal temperature probe. If it does have one, it doesn't seem to work properly, and it certainly isn't mentioned in the manual for the KAIWEETS meter. So I think that this temperature display at the moment is a rogue and it's maybe some kind of a bug. Now I can see it also displays the temperature on the 600 amp range. It's displaying it on the voltage range. Doesn't display it on the frequency range. Again, it displays it on the ohms range, and when we do select the actual temperature range here, we can see that it does actually again display the temperature. It's got Fahrenheit at the top and then it's got Celsius at the bottom in large characters. But I also think that this temperature indication is incorrect because I don't have the thermocouple probes plugged in at the moment, so let me go ahead and do that. Now it's very important that you plug the probes in the right way round. Now I do actually think it would be better if the terminals on the bottom of the meter, if they'd actually been marked red and black. They have actually got common and input marked on the top of the unit here, but it would be far clearer and easier to make out if these were actually colour coded. Now I can see that unfortunately the ice is somewhat melting on my gin and tonic, but let's go ahead and stuff our probe in here, give it a bit of a stir, and we're getting a temperature indication of about 1.1 degrees, 1.7 or 29 Fahrenheit. I'm guessing that's correct. I don't actually have any calibrated way of testing this. Just using my soldering iron now to try to test the upper end of the temperature range. Now I've got my soldering iron set to 360 degrees. Of course it's not going to be very accurate, and the KAIWEETS meter is measuring, well, it's 384 at the moment. The maximum temperature display is specified as 1000 degrees. I'm wondering how hot we can go with a bit lighter here. Well, certainly the thermocouple's now on fire, so I'm guessing it gets quite hot. So that's up to 840 degrees. Now unfortunately I can't check the accuracy of the temperature measurements, but when the temperature range is selected and the thermocouple probes are plugged in, the actual indications do appear to be correct. However, when the meter's set to the other ranges and we're using this dual display, it does appear that whatever temperatures are displayed here are just nonsense. So on the side of the instrument here, we've got a dual function push button. So if you press the push button once, what that actually works as, it's a hold function. So if you're actually taking a reading, but maybe you can't actually see the display on it, what you can do is you can take your reading, you can press the hold, and that'll take a snapshot of that reading. So it's now holding that figure, it's holding the reading on the display here, so you can look at it at your convenience. Now if you actually hold the button again, or press it again, you can see that an LED lamp comes on the front of the instrument, so that's an LED torch, and of course that's useful for those people that like to carry out high voltage current and voltage measurements in darkness. And finally, the KAIWEETS meter does have a non-contact voltage detector, so if you just switch that on, we get the words NCV displayed here at the bottom. And if we actually bring a live wire close to the clamp jaws, because that's where the actual detector is, you can see it starts bleeping. And if we move the wire away, it stops. And I've also noticed that we get the red and green indicator, which is probably giving us some indication of how close the actual cable is. So we get a green indication first, and that becomes a bit more urgent as we bring the cable closer. And I have to say, that feature does actually appear to work really well. Well, in summary, what do I think about the KAIWEETS HT208D? This meter is currently listed on Amazon at £79.99, so I don't consider this as a low cost meter. I believe the construction quality and also the feel of the meter is very good. It feels like a quality product. The selector switch on it is very positive, but one thing that I have found, it's a little too small and it can be difficult to get hold of. I think that the OLED display is absolutely beautiful, but I did find that it could be washed out in daylight conditions. Generally the viewing angle of the display was good, but I did find that under certain side-on conditions it does have a tendency just to blank out. The test leads that come with the KAIWEETS meter are of a very nice quality, and it does use silicone rubber leads. Now it would actually have been nice if they'd actually printed the specification on the leads themselves, but they are good. The quality of the plastic moulding on the probes and also the connectors is very good. The only improvement that I would like to see is actual probe tips themselves could have been sharper. Based on the testing that I could do, I thought that both the 1000 amp and the 600 amp AC and DC current ranges, they did appear to be very accurate. I did find one problem with both the 600 amp and the 1000 amp ranges which really concerned me, and that is if you've got a voltage source connected to the meter, it actually affects the current measurement range. Now of course when you're actually measuring the current, the fact you've got a voltage source connected, it should have absolutely no effect. It shouldn't affect the current reading at all. So really what needs to happen is when the meter is switched into the current range, these input terminals need to be somehow disconnected. Now I think that most amateurs who purchase this meter, they won't actually be interested in measuring these high current ranges of up to 1000 amps because we don't encounter them in a domestic situation. If I did want to measure 1000 amps, I would probably still buy a Fluke or something like that just for the additional confidence factor and safety ratings. So I think the most likely people to purchase this are probably still people that are interested in domestic type installations, and basically this current range is a little bit too high, and I certainly would have appreciated the ability to actually measure very low currents to find faults like earth leakage faults. And you would also find that most lighting circuits are now using LEDs as opposed to the old-fashioned incandescent lamps, and these LEDs only draw a small amount of current, so the fact that this meter doesn't read anything below 100 milliamps, well, I think that could be a problem for some people. Moving on to the voltage range, I actually thought the accuracy of both the AC and DC ranges was absolutely excellent. I found that in all circumstances the actual frequency measurement was very good, but when you use the dual display and get a frequency measurement on the current ranges, the fact that it doesn't start until 25 amps, well again, most domestic installations would never see 25 amps, so again I thought that could be a problem for some people. The ohms range, the diode test and the capacitance ranges all work flawlessly, no problem there. Now the only function of the KAIWEETS meter that I didn't like was the temperature measurement, and that was really related to this dual display. So in some of the ranges it does actually display a temperature, but that temperature display is just meaningless and it doesn't do anything. It doesn't even work properly when you do plug the thermocouple probes into the meter, so KAIWEETS either need to remove this dual display function or they need to make it work. Moving on to the low Z voltage range, I can really see that that would be really useful for determining whether or not you were seeing ghost or phantom voltages. Moving on to the non-contact voltage detection, that really did work very well and had an excellent range. So overall, would I recommend the KAIWEETS meter? Well, actually, yes, I would recommend it. I do think it's exceptional value for money, but unfortunately for today, I'm actually only going to give it a rating for 7 out of 10. The reason it's going to drop some points is because this temperature display, the dual temperature display, just doesn't work properly, and it would be easy for KAIWEETS to fix that. But the more serious problem with having voltage sources connected on the current range and the effect that has on the reading, I think that is a problem, and again, that needs to be addressed. However, I think for today, that'll do. So as always, thanks very much for watching. I hope to see you again very soon. Until then, bye bye for now.